Now, it turns out, I mean, and just like yesterday when we saw that there was two tones, when you put in a two tone input, they would interact with each other and cause intermodulation. Well, the same thing should be expected even in the third order nonlinearity case. It turns out that things are a lot more serious here, as the intermodulation products actually fall very close to the input tones, as we will discuss going forward. So, again V out is A1 Vi plus A3 Vi cube, and Vi is, let us say, A cos 2 pi f1 t plus A cos 2 pi f2 t, all right. And so, V out therefore is A1 times Vi, where Vi is what we just wrote above, plus A3 times A cube times cos 2 pi f1 t plus cos 2 pi f2 t, the whole cube. And what does the cube look like? So, it is basically cos cube 2 pi f1 t plus cos cube 2 pi f2 t plus 3 cos square 2 pi f1 t cos 2 pi f2 t plus 3 cos 2 pi f1 t cos square 2 pi f2 t, right. Before we go out and expand all this stuff, let us figure out what we should expect to see. We should expect to see the usual gain compression terms, right. We should also expect to see third harmonic distortion, correct, okay. And what is that? And we should also now expect, based on our experience with the second order nonlinearity, we should also expect to see that the two terms will interact with each other through that third order term, and these are the cross terms, right. Right, where the two tones interact with each other through the nonlinear. So, let us get started. So, V out is A1A plus 3 A3 A cube by 4 times cos 2 pi f1 t plus similarly A1A plus 3 A3 A cube by 4 times cos 2 pi f2 t, right, plus A3 A cube by 4 cos 6 pi f1 t plus A3 A cube by 4 6 pi f2 t. So, these are all terms that we are familiar with, right, gain compression plus third harmonic distortion of the individual tones, right. And as you might imagine, in the second order case, the distortion terms were typically not important because they can be easily filtered away, right. But what you cannot get rid of is basically the intermodulation terms, and that is what we are going to see next. So, remember that cos square theta, 2 cos square theta minus 1 is cos 2 theta, right. So, you basically have 3 by 2 times
cos 2 pi f2 t plus cos 2 pi f2 t
cos square 2 pi f1 t is nothing but cos 4 pi f1 t plus 1 into cos 2 pi f 2 t plus of course, the other term where we interchange f 1 and f 2, cos 4 pi f 2 t plus 1 times cos 2 pi f 1 t, right, and we will simplify this one and the other one just simply follows. So this is nothing but sorry, we have forgotten an a3 a cube, a3 a cube, a3 a cube, just a3 a cube, right. Okay. So, now we will multiply this by 4 and take that stuff in there, and this is basically a3 a cube times 3 by 4 times 2 cos a cos b is cos of 2 pi times 2 f 1 plus f 2 times t plus cos 2 pi times 2 f 1 minus f 2 times t, right, plus what do we see here, a3 a cube times 3 by 2 cos, that's what I am saying. So, if this is nothing but plus 3 a cube times a3 by 2 cos 2 pi f 2 t, right, and this we can add off to that to the fundamental later, right, and so what else, so if you do the same thing here, this will simplify to 3 by 4 a3 a cube times cos 2 pi into 2 f 2 plus f 1 into t plus cos 2 pi 2 f 2 minus f 1 into t, right, plus 3 a cube a 3 by 2 times cos 2 pi f 1 t, right. So, okay. So, the fundamental terms, the fundamental frequency amplitudes are approximately a1 a n, for both the tones are a1 a. So, the input tones, basically if you plot on a picture, the input tones let us say are f 1 and f 2, right. The output tones okay, are what all are the output tone frequencies. So, f 1, so there is f 1, f 2, there is harmonic distortion which is basically 3 f 1 3 f 2, right. There is 2 f 1 plus f 2, right, which is basically if you assume that f 2 minus f 1, you call that delta f, right. So, 2 f 1 plus f 2 is nothing but 3 f 1 plus delta f, correct. So, you will have 3f1 plus delta f and if you have 2f1 minus f2 is nothing but
F1 plus delta
2f1 minus f2 is nothing but 2f1 minus f2 is nothing but
F1 minus delta F.
f1 plus delta f, which therefore is f1 minus delta f, right. So, remember that this is delta f, correct. So, now you have an intermod tone which is here and this is 2f1 minus f2, correct. So, we have seen this, we have seen this. Now, we have 2f2 plus f1, right, and where does that, so 2f2 plus f1 is nothing but 2f2 plus f2 minus delta f, this is f1, correct, which is nothing but 3f2 minus delta f. So, that is going to be sitting here. So, that is 3f2 minus delta f. Okay. And the next thing is that you have 2f2 minus f1, 2f2 minus f1 is nothing but 2f2 minus f2 minus delta f, which is f2 plus delta f. Right. So, these tones are all in the vicinity of, I mean if f1 and f2 are close, these tones are all in the vicinity of 3 times the average input frequency, right, and therefore, can in principle at least be easily, yeah, in principle can be eliminated by filter. Okay. All right. And unfortunately, these tones, they lie very close to f1 and f2. So, these are intermodulation tones and cannot be filtered. Right? And these are the most important tones that one has to worry about when one is talking about. In a lot of systems, these can be, as I will illustrate going forward, they can be really problematic. So, I am going to let us just focus on the tones which are the intermodulation tones that are next to the input. So, this is f1, f2, this is 2f1 minus f2 and this is 2f2 minus f1. The amplitude of the fundamental is approximately A1A. So, where we assume that you know you are operating sufficiently linearly, so that compression is not an issue, and these are intermodulation tones whose amplitude is 3 by 4 A3 A cube, this is also 3 by 4 A3 all right, and this ratio is called intermodulation distortion because of third order nonlinearity. So, this is called IM3. So, IM3 therefore is nothing but 3 by 4 A3 A cube divided by A1A, which is basically 3 A3 A square by 4 A1. And if A increases by 1 dB, IM3 will increase by 2 dB. All right. So, if I plot the input amplitude on a log scale and the output amplitudes whatever they are also on a log scale, the fundamental amplitude will basically do again something like this and then will compress and do something like that, and this slope is 1 dB per dB. Okay. Now, the intermod component will have a slope which is so this is the fundamental tone or the strength of the fundamental, and this is the strength of the intermod.
Fundamental will include the compression term also. Fundamental tone.
Yeah, if the input amplitude is very large, then you will start to see compression in the fundamental output also, right? And so, this the intermodulation tone, the strength of each one basically will keep increasing with at 3 dB per dB, right? And at a given amplitude, what represents the IM3? So, at any given amplitude, this distance is basically IM3 in dB. All right. And and just like how we had IIP 2, which was a number that quantifies how linear the amplifier is. By the same token, if the amplifier was perfectly linear, then this if you extrapolated this line, right, and this line, these two lines will intersect at some fictitious point there, right. If the intermodulation distortion was lower, what would happen to the to that point?
It will be at a lower amplitude.
No, if the intermodulation distortion is lower,
Then it will be very high.
then the point of intersection will move towards the right. Okay. So, so this therefore is a fictitious point, which is the key point is that this is a fictitious point where intermod tone is the same as the fundamental, right. It does not mean that you go and put an amplitude of that value and you will get the same fundamental and the intermod tone. It is obtained by measuring the amplifier or the nonlinear block with very small signals, right, and measuring both the fundamental and the intermod tones, right. You measure it for a few amplitudes. So, for example, let us say maybe you measure a few amplitudes here, right, and then you will get a straight line for each one of these things, right. If you do not get a straight line, that basically means that you are already in compression, right. So, or the system is not weakly nonlinear, and so therefore, you produce these lines and they will go and intersect at some point there, and that is the this point is therefore called the input referred intercept point for the third order intermodulation distortion, right. So, IIP3 is when or rather AIIP3 is when 3/4 A3 A cube equals A1 A, which means A is 4 A1 by 3 A3 under root. Right. In other words, the moment you know the gain of the amplifier and you know the IIP3, you will be able to go and figure out what that A3 is, which basically means that it will also be able to, I mean, remember that HD3, the harmonic distortion and the intermodulation distortion are basically coming from that the same A3. So, if you know one, you will be able to calculate the other and so on, right. See, one advantage of an intermod measurement over I mean, even if you want to measure harmonic distortion, it always makes it's easier from a measurement point of view to what do you call it's a more accurate measurement to measure the IIP3, or rather not the IIP3, but to measure the intermodulation distortion and then infer the harmonic distortion from intermod rather than the other way around, because if you have an amplifier which is producing a third harmonic, by the time the third harmonic, I mean the fundamental and the third harmonic go through different paths, right, will have, I mean they go through the same physical path, but the physical path may have some frequency dependence. So, the higher order harmonic may get attenuated by the time it goes into your measurement instrument, right. On the other hand, with intermod there is basically no way you can make an error, because if you take two closely spaced tones, the intermod tones are just next to the inputs, and therefore, whatever happens to the fundamental, the same thing will happen to the intermod tone, and therefore, when you measure you will be able to get an accurate picture of what that A3 by A1 is, right. Now, why is intermodulation so important in a whole lot of systems, particularly in RF? Well, it turns out that in an RF input spectrum, I mean, as you all know, spectrum is very expensive. So, you will have very closely spaced channels, and the use case scenario in RF is that your desired signal is very small, right, and you have interferers that are unwanted. Okay. And the spacing between, so these are adjacent and alternate channels. So, this is called the adjacent channel. And this is called the alternate channel. Okay. And the spacing is the spacing between channels is obviously called the channel spacing, right. Now, of course, the RF spectrum can be will have multiple channels, because there are lots of customers who are probably using the phone at the same time, and in your cell they better be in your neighborhood, they better all be using different channels, otherwise they will affect each other, and therefore, right. So, the RF spectrum, this is the representative RF spectrum, and let us say this goes into a front end amplifier. We have already seen earlier why you need a front end amplifier, because the input signal is so small that it has to be amplified before the next stage can make sense of it. And of course, this amplifier is made with active elements, and therefore, this is at best it is weakly nonlinear. Okay. Now, if this got and due to third order nonlinearity, what do you think can happen? Well, these two, the adjacent and the alternate, will intermodulate, right, and cause some junk, right, here. Okay. Likely, and similarly, these two will intermodulate and cause another signal which directly falls on the desired signal, right. So, our desired signal can get terribly corrupted by intermodulation distortion from alternate and adjacent channels, not merely alternate and adjacent channels. Let us say you have one channel here which is very large, right, and another channel which is here which is even larger, and these two can also intermodulate and cause distortion, right. But in principle, those are easier to handle, because you can put some kind of narrowband, some kind of filter which can remove stuff which are very, very far away, right. But the close in the alternate and the adjacent channels, you can't remove by filtering, correct. So, the amplifiers and the signal chain has to be linear enough to be able to process such signals without causing sufficiently large intermodulation distortion so as to corrupt your signal completely, right. And the point is that the desired signal is very, very small, and the undesired signals can be several orders of magnitude larger, right. And therefore, even a small amount of nonlinearity can cause the remember, the intermodulation distortion is proportional to if these two tones, the intermodulation distortion is proportional to the strength of the interfering tones, which can be very large compared to your desired tone, right. So, so therefore, even a small amount of distortion, intermodulation distortion, can potentially completely mess up your desired signal, all right. So, so a lot of this, as you can see, is just merely jargon. There is nothing, you have to be aware of the fact that you can have intermodulation distortion, right. And of course, there is a whole bunch of formulas which you can derive at any time. There is nothing what you call fundamentally difficult about, conceptually difficult about intermodulation, or basic nonlinearities. In the next class, we will basically move on to what happens when you have all these concepts apply to networks which are memoryless, correct? Okay. So, now the question is what happens when you have weakly nonlinear say transconductors and so on with capacitors and so on. I mean, for instance, we have seen filters, right, where we have op amps and then capacitors and so on, and of course, the op amps are made with voltage controlled current sources which are all transistors, they are all nonlinear. So, we have to figure out what happens with what happens when those are weakly nonlinear and how they affect how to analyze circuits like that. We will continue in the next class.